Bonjour tout le monde.
Hello, everyone.
Merci d'être venu malgré
Thank you for coming despite the long weekend. I'll be speaking briefly. I will just
sur les problèmes d'optimisation.
point out optimization problems, coming back to what Yann Olivier spoke about at his last lecture. I'll speak for about 25 minutes, and then we'll have Cordelia Schmidt from INRIA and Sami Benjo from Google Research. I'll be speaking about optimization and geometry in the space of neural networks. I've already spoken about it, but I think we need to recall a few principles.
On a parlé de Yann Olivier la dernière fois.
As Yann Olivier said the last time, when you use
Par gradient.
minimization by gradients,
Dans le cas du gradient,
in the case of a batch gradient, you can always calculate
pas de gradient optimal.
an optimum gradient step in a simple dimension. Just write that
Lorsque le
whenever
coût est quadratique,
the loss function is quadratic, to determine the gradient step taking you directly to the minimum, all you have to do is to inverse the second derivative, the curve, therefore, of the loss function.
il y a un pas gradient optimum.
So there's an optimum gradient step for batch gradients, not stochastic, and in one-dimensional cases. If it's multi-dimensional, it's just several one-dimensional cases,
Dans un espace qui est
but not in a space that's easily identified. You can have rotations with respect to the representation space. If you take two entries and you train for classification by the least square method with a binary variable to predict +1 - 1, and you take the scalar product between the entry and the weight vector, you have two classes with a Gaussian distribution with a specific mean, but the total mean is 0. In this case, the Hessian matrix is simply the covariance matrix of the input vectors. That's easy to demonstrate.
il s'avère que la fonction
It just so happens that the loss function has this shape. In the weight space, the two weights that you find here in this unit. The reason why the curve is greater in this direction than the other, these are ellipses, the lines of constant loss. So the curve is great in this direction because the variance of data is more significant in this direction than the other one. It's as simple as that.
et donc comme la variance est plus élevée,
Since variance is greater, that gives a large term, an eigenvalue in this covariance matrix that's important in this direction and less in the other direction.
propre de ces ellipses,
The eigenvalues correspond to the eigenvalues of the covariance matrix. Here we use the batch gradient to see how it works with a weak gradient step. Each pass on the learning set, you change colors to show how convergence works. So this is a relatively small gradient step enabling convergence. But here, the gradient step is bigger. So it diverges in one direction but converges in another. But that doesn't help us much. If we move on to a stochastic gradient, this is the batch and here the stochastic gradient. Here, at each pass, in the learning set, we do more than just an update. So it progresses much more quickly due to data redundancy.
stochastique
So stochastic
converge beaucoup plus vite, particulièrement pour l'ensemble d'apprentissage.
well, converges faster with a large learning rate. But at the end, unfortunately, there are fluctuations. To reduce it, you'll have to reduce the gradient step or use techniques such as momentum techniques or average SGD methods, so as not to bring at the end as a solution the last configuration of the weight vector, but a sort of moving average of the previous configurations over time.
Alors donc, ce que ça montre tout ça, c'est que si on
All of this shows that if you want to quickly converge. You would need different gradient steps in each direction, but that's a bit difficult to do because the directions are not aligned to the axis, meaning inversing the covariance matrix, and that would work only if the function is convex or almost quadratic, which is not the case for multilayer networks. So that's it for multilayer networks. The simplest network you can imagine: one input, one hidden unit, and one output. And we'll just learn to calculate the identity function using the least square method. Very simple. One training example. Input is 1, desired output is 1. So the loss function is 1 minus the output, which is 1 multiplied by W1 multiplied by W2. So that is the loss function. So the simplest function you can imagine with layers. Here is the shape of the loss function. These are the lines of costs equal. I lied a bit. This example in particular, there's a sigmoid in the middle. In this example, which is a 3D representation of this, here there's no sigmoid in a way. The solution is a hyperbola. Clearly, for the output to be equal to 1, W1 should be equal to 1 value, and W3 equal to 1 and this value, giving us a hyperbola solution. So two local minima. But the local minima are equivalent. By symmetry, you can choose one or the other, it doesn't matter. Each time you have a symmetry, you can exchange W1 and W2 without changing the result, just like having several weights. If you have several hidden units, you can exchange two hidden units while keeping their weights, creating a symmetry, which would change nothing about the solution. Clearly, between both, there's a saddle point. Each time you have a symmetry, there's a saddle point. And since you have a lot of symmetry in large networks because of the combinatorials of changing units, that leads to a situation where the number of saddle points in the loss function of a multilayer network is huge. Here's what it looks like. Here's what the convergence of the stochastic gradient looks like for this simple thing here with a sigmoid in the middle. If you start here, quickly you find a solution. Starting here, because it's flatter with the sigmoid, it takes longer. And you have this amusing phenomenon where, depending on the starting point, you'll have different local minima. So it doesn't matter which local minima you find because they're both equivalent. This argument was used against neural networks, multilayered neural networks in the 90s. People said it's not convex, so there's no guarantee that the system will converge. In fact, it just so happens that there were a lot of studies that aren't quite formal yet, but they're beginning to become formal, showing that the geometry of the loss function in high dimensions are such that you have a lot of saddle points, but all the local minima are equivalent, more or less. I'll show you examples on attempt to prove this formally with horrible approximations, so it's not very formal, but I will show it to you anyway. If you take a multi-layer network as we use them today, a series of matrices, you have an input multiplied by a matrix, and then we have a ReLU function, the max of x0, which may be viewed as a sort of switch, choosing between not connecting this unit may be in this zone if its input is negative, or in the linear zone. We can simplify the problem and view it in an interesting way. The input and output functions of this output may be seen as a sum over all the paths of the contribution of each path. If you take the input-output relationship between 3 and the output, there are many different paths between both, and each path contributes the input multiplied by all the weights along the path, and all of this is added. All these contributions are compounded literally at the end. There's a little complication. Some of these paths will be deactivated because one unit along the path is in the flat zone. So there is a sort of binary variable of activation that will determine this, but we can write that the output will be the sum along all the paths of an indicative value, indicating if the path is activated, depending on all the weights and all the inputs, unfortunately, but we'll see about that later on, and then the product of all paths along the weight, and you multiply that by the corresponding unit. So inputs and outputs summed up over all the paths. A sort of W polynomial, W the number of weights, with the difference that you have this indicative function that is a bit of a problem. It doesn't exist, though, if the system is linear. Of course, we are interested in the loss function. If you use a loss function, which is a sort of ReLU in itself, choosing the desired output, you can write the loss function the same way, except that this indicative value takes into account now the desired output. We end up with something like this. The loss function is the sum along the paths of the product of all weights along the path multiplied by a variable, taking into account the input, and which may be 0 in cases where the path is not activated. It's a sort of collection of polynomials in a way, and that are enabled depending on which set or subset of this is enabled. There are theoretical results in the theory of random matrices and the properties of this type of polynomial. Unfortunately, in cases where the coefficient is Gaussian, as taken from GOI. In this case, statistics on saddle points and local minima of these functions can be calculated insofar as we have a large number of variables. In physics, or in probability, this is what is known as spherical spin glasses. These findings, I won't go into the details, but based on Gérard Benarous's articles, the director of the Institute of NYU, who was at École Normale before, he showed that the number of saddle points in this type of function is truly huge, and showing that all local minima have a value for the objective function, the function in question, which is very narrow. In other words, if you look at the histogram of the number, well, depending on the level of the loss function, how many local minima have a specific energy? They're all in a very narrow band. Therefore, all local minima are almost equivalent. It doesn't matter. You will find one, you never know which one, but the one you find doesn't matter. They're almost all equivalent. There are a certain number of local minima with a higher energy level, but they are very few and far between, and the likelihood of finding that is extremely weak, exponentially weak. We can verify that when you train neural networks. This is a neural network with hidden layers, and you vary the number of hidden units. You can see that when you repeat the experience hundreds of times, with MNIS reduced to the dimension 10 by 10, we end up with a histogram. This is the histogram of the values of the loss function for the solution obtained by learning, by relearning many times using different starting criteria. The energy level is extremely close. You always obtain solutions that are relatively equivalent in terms of the energy level. What's more interesting is that even if they are a bit different, In terms of the generalization error, the error on T7, there's very little difference.
Et la différence est d'autant plus faible que le réseau est...
Especially if you have a large network.
C'est un peu contre-intuitif.
Which is counterintuitive in a way, because statistics would tell us that the bigger the network, the more the problem of over-parameterization and a greater disparity of errors on T7, but that's not the case. We see that T7 errors are concentrated as the network becomes bigger, which is odd. These are the theoretical results, but I'll skip that. I will speak very briefly about a technique used, well, that started to be used largely for large-scale optimization of, let's say, large-sized neural networks, and I'm referring to distributed optimization for training a neural network on several machines. There are different ways of doing that. I have a simple idea that dates back some time ago. The first experiments was by Roger Benjou in the 90s, but you had people at the start of the 90s in Germany and Switzerland who were working on parallel architectures, implementing neural network. Hertz-Miller, for example, in Zurich, at the end of the 80s, start of the 90s. So it was a hot topic at the end of the 80s, and it fell out of fashion. Now it is fashionable again, and we have lots of GPU cards for large neural networks. You just divide the training set into pieces. You give a chunk to each processor or each node, a cluster, for example. What each machine does, each machine calculates its gradient on a mini-batch. They all do that at the same time and communicate their gradient to a central server. So it sends the gradient, sends it to the central server, which averages everything and redistributes a weight to all the CPUs or GPUs. This is what we call data parallelization. The network itself is not shared. The data is shared. There are two ways of doing this. Synchronously, where everyone does it at the same time, sending the gradients. They wait for all the gradients to arrive, update the parameters, and send the parameters. And they wait until they receive the parameters before moving on to the next mini-batch. If you have a low delay communication structure, it works well. But there are limits with respect to the number of machines you can use. These are GPU boards in the same machine. If you want to do this on several machines, that would cause for a low delay, fast communication system for this to be interesting. Secondly, you can't go below a certain size of mini-batch per GPU. Typically, the size cannot go below 16 or 32, otherwise you lose efficiency, meaning that when you multiply the number of GPUs on which you do parallelism, you end up with large mini-batches, and that's no good for optimization. The result is not as good as if it's too big, because it cannot benefit from the fluctuations with regularization, and you cannot benefit from the fact that the stochastic gradient is faster than the batch gradient, because you end up with large batches. There's an asynchronous variant where the individual nodes send their gradients without waiting for the results. They keep on working. From time to time, they receive the results. And variants where, well, this is what you call asynchronous SGD. What we propose is an elastic, well, this was published in Nice this year, elastic average SGD, a very simple technique as well, where individual nodes do not communicate gradients, but communicate weights. Each node fully optimizes the problem on its data. The difference between each node is that they see data in a different order. They don't all do the same thing. They do different things. They all have all data. They carry out a certain number of updates, mini batches, and if time permits, they send to the central parameter their local weight. They send that to the central parameter server, which is updated with the local weight. Now, of course, the problem is that nothing is there to prevent the nodes from diverging from each other entirely. So use a regularizer, a sort of elastic term saying that each individual cannot go too far away from the last value they obtained from the parameters. It's a loss function like this, where each worker in each node, so everyone, they all minimize their loss function in a way. And you have an elastic term which attracts the parameters of each box towards the central parameter, the x tilde here. And from time to time, as I said earlier, each node sends a weight to the central parameter server, which updates its own parameter vector. But a small update. The update rule is something like this. Each node is updated with a simple gradient, but with a regularizer term, saying don't go too far away, though, from the central parameter. This value is updated in the worker only from time to time, and the central parameter is updated as well from time to time. By calculating, by being attracted, let's say, a sort of attraction force towards the mean of all the weights of the other nodes. There are several parameters to be identified, but I won't go into the details. There's one variant that works very well, where you use momentum SGD in each worker. It's better than if you use a normal SGD, actually. Leading to significant accelerations with 4 processors here to train a large convolutional network on the ImageNet database. So very efficient and used in production by Facebook and also by other companies, I believe. Well, or similar things at any rate. Badu, I believe they also use it in production as well. I don't know about Google. I think Google, they use techniques like asynchronous or synchronous SGD, I think. Downpour is from Google too. A sort of asynchronous SGD. I will stop there and give the floor now to Cordelia Schmidt from INRIA.